Recording is. Good. All right, so hi everyone. Thanks for coming here today. So today we have Hoai-An from CMU giving a talk about so sketching for maximum coverage. And Hoai-An is around today if you want, people wanted to chat with her later today as well. All right.
Thank you. All right, yeah, I'm Nguyen. I'm a second year at CMU right now. This is going to be sketching for max coverage, and then I'm going to talk about some applications to fingerprinting. Hopefully, we can have time. This is joint work with Nguyen, Alessandro Costa, Hoai-An, Nguyen, David Woodruff, and Kevin John. So what is maximum coverage? We have n items in our universe, and we have d subsets of these items, okay? And the goal is that we want to find k subsets such that they have the largest union size. In other words, we just want to find k subsets such that they cover the most distinct elements among them. So if we see it, we can have items, for example, on the left, our subsets on the right. And okay, so item A is in subset 1, items B, C, and F are in subset 2, and so on. And let's say for k is equal to 2, well, what is the right answer here? We can see that it's subsets 2 and 4, right? I've picked 2 subsets, and actually I've covered every single item that can be covered in this instance. D cannot be covered by anything. Cool. And this is a pretty well-studied classical problem. There's a lot of applications in sensor placement, and then you also have reference maximization in a lot of other settings. So before I go further, I'm just going to formalize the input in 2 different ways. You can think of it in either way. That's to help you and also to sort of help with the rest of the talk as well. So the first way, which we just saw, is you can think of this as a bipartite graph, right? And I have an edge between ij if item I is in subset j. Equivalently, I like to think of it as in a matrix way, which I know some graph people do not like, but you can think of it as an n by d matrix A, and really all we have here is the adjacency matrix, right? The only difference that I'll just point out for now that will just be important later is for max coverage, it's standard to just use ones and zeros, right? Either it's covered or it's not covered. But we're actually going to allow in our setting for any non-zero element to mean that it's covered. This will work for our applications, and it's just sort of more general, right? You can have anything, the zero doesn't mean it's not covered. Okay.
Sorry, what does that mean? So 0 means not covered, anything else means covered.
Yeah.
Okay.
For the purposes of the max coverage part, you can just think of it as ones and zeros. But for the applications, it'll be sort of important why we allow other.
But it doesn't mean you cover it twice, right?
No. Yeah, just any non-zero means it's covered.
Just the way that it's covered, the importance of coverage or something.
Yeah, exactly.
Yes.
Okay, so I'm just going to present a simple greedy algorithm. This is the classical algorithm. What do? Okay, we initialize our output set. And we go for k rounds. And every single round, we just take the subset that gives me the largest marginal gain. Okay, and this gives, a 1 minus 1 over e approximation, and this is actually provably optimal for polytime algorithms unless p is equal to np. And just to show you, okay, so what is the subset that has the largest marginal gain in the first round? Well, it's 2, because I can cover 3 things. Okay, and what is the next subset that has the largest marginal gain in this setting? It's 4, and you can see that this is the exact same answer that we had at the first slide too. Okay, so this is basically an OKND time. So I have k rounds. I essentially have to go through my entire graph in each round. And then for my space, it's ND space. And so in general, this is a pretty nice algorithm, right? I have an optimal approximation factor, I have polytime, I have linear space. But the focus of this talk is of course, can I do better than this? And in general, we're going to try to focus on getting sublinear space. And this is going to bring us to the streaming setting. First, does anyone have any questions about max coverage, the formulation at all? Okay, well. All right, so the very,
I'm curious about that 1-1/3, because that sounds like expected case thing. Just curious, that's
Oh.
all, it's just a weird question.
it's like,
The optimal 1-1/3 approximation, 1-1/3 is more likely to show up in expected case things than in any guarantees. Just a comment.
oh, okay, yeah.
No, there's no depth.
No, that makes sense, yeah, this is actually the first problem I've worked on that had such a, like, guarantee, but,
Yeah, but it's,
yeah.
it's, if you choose n numbers between 1 and n at random with replacement, that's the fraction you expect to get. So it probably comes out the same, doesn't matter, don't worry.
Okay, thank you. Okay, so here we're gonna focus on turnstile updates. So you can think of each update is gonna be ij, and it's gonna be either +1 or -1. And all this is saying is, remember our matrix representation before, we're just gonna update one specific entry of this. Equivalently in the graph model, this just means that I'm like getting an edge or I'm deleting an edge from my graph. These updates are gonna come one by one in a stream. And the goal is that I want to process the stream in sublinear space and ideally a small constant number of passes. For actually the rest of this talk, we're only really going to talk about one-pass algorithms. And, you know, just we generally assume the length of the stream is Hoai-An. This is not super important. It's just so we don't run into like bit complexity issues. All right. So let's talk about some existing upper bounds. Again, I'm only going to focus on one-pass algorithms. There's also a ton of work outside of streaming, but I'm not going to talk about it. Yeah.
So like, we start with the actual given A, and then we get like updates one by one, and we want to find what do we want to find? So I don't understand why what aij equals a plus minus one.
Yeah, so this is just the model. So if you think about the matrix representation that we had before, so the usual representation is you start with A and everything's initialized to 0. And then you're going to get a stream of updates, and each update is going to say, okay, increment the ij entry by 1, or like decrement it by -1, or decrement it by 1. And then you're just going to have a bunch of these streams, and your streams is going to be like some polygon. And then at the end of the stream, now you want to output your answer. So like now you want to output k subsets that have the maximum coverage.
And you start with all zero.
Yeah, usually that's the usual setting. Although like, I mean, you could start with anything if you wanted to, and then just apply updates on it.
You got me confused now. As you're going through there, I would assume that you should go through there, you get it, you're told what's in the different subset each time. But you're getting changes in the subsets?
Yeah, so I'll mention in a second in the previous work. So the most typical setting that was first studied is like settle. So this sort of entails what you're talking about. Like in each update, I sort of get a subset and all of the items in its subset. But we're saying we want to study an even like stronger model, like or a more general model. And actually, I can just individually insert or delete items into subsets. Does that make sense?
One question, is
Yeah.
the problem much easier if you only need a succinct representation of the matrix A? I mean, the A is given you all in once, and you create a much maybe sparse or succinct representation of A, and then you use A to solve the maximum K coverage problem. The only difference is you don't have to do the streaming.
So you mean like if I just have direct access to A? Or
And then you try to create a succinct representation of A, and then you try to use the succinct representation to solve the K coverage problem.
oh, okay, I see. Actually, this is going to be similar to what we're doing. So like I'm going to talk about linear sketching. So basically we are going to linearly sketch A, and essentially we're going to like compress A in some sort of way. Like the representation of A so that we can output an answer at the end. I'm not sure if that's your question.
Yeah, that's the one way of doing it.
Yeah.
If you can do scripting of stuff, you can use it to translate apart.
Yeah, I just also mean that because we're going to talk about sketching, and I'll introduce what a linear sketch is completely. Like, you don't have to apply a linear sketch in streaming. A linear sketch is just like a nice device that you can apply updates to, but also like if you were just given A, you can just sketch A, and this is sort of like a compressed version of A that you can now answer the question on as well. Okay, so for existing upper bounds, the first work that we're going to sort of talk about is McGregor and Vu from 2018. And, similar to what we just talked about, this is going to be the insertion-only set arrival. Okay, so there are no deletions, we only have insertions. And furthermore, every single update is going to reveal a subset in all of its edges. Okay, and equivalently in like my matrix model, right, each update is going to reveal like an entire column of A versus like just like entries. And you can see here that they get like a near optimal approximation factor, right? They're only losing an epsilon here. And the space is O tilde D over epsilon squared. And the second work, which is, this was concurrent work, is from Batani, Ifan, Diri, and Mirconi in 2017. This is going to be a stronger model. So we are in the insertion-only edge arrival model. So what this means is that I still don't have any deletions. I'm still only having insertions, but I don't see each subset in entirety. Now I'm seeing each edge individually, or again, each like entry of A. And they match the approximation factor, and they almost match the space up to like an epsilon factor. And for the rest of this talk, I'm just going to be suppressing like polylog factors to not clutter everything, but that's what the tilde is hiding. All right, and then, there's been a bunch of other work if you consider like different approximation factors, or you have like random arrival streams. So now let's talk about lower bounds. So the first one is from Asadi 17, and it says that if you have, or for any constant number of passes, if you want a 1 plus epsilon approximation, well, this requires D over epsilon squared space. NV18 show that in a constant number of passes, even if you have unlimited like processing time, right? So like anyway, it actually doesn't matter too much. And it says that if you want even slightly better than 1 minus 1 over E, then you need like omega D over K space. This sort of means that the previous work is, for constant K, basically optimal. And the BM paper says that if you have some multipass, you want a 1/2 plus epsilon approximation, well, you need like omega D total space over all passes. Yeah.
That's the question. Why is the approximation factor bigger than one of the first? Yeah. One minus.
Yes, sorry, there's
Yeah, no, it's not.
It's my fault, I never write that approximation, I'm always more conform.
Ah.
So everyone else is some of that.
Okay, so what do we get in our work? So now we're in the fully turnstile model, right? We're in or you can think of it as a turnstile edge arrival also. So first, we're incorporating deletions. And again, we're in this edge arrival model. So we're, again, inserting or deleting edges from our graph. Or equivalently, we're like adding items or subtracting them from subsets in each update. We match the approximation factor, and then we basically match the space. Again, we're different by an epsilon factor. Cool. So why are deletions important? For a number of reasons. First, it was like really critical when we wanted to apply this to some of our fingerprinting things that I'll talk about later. You can think of it sort of in some natural applications. Maybe I want to remove faulty or noisy data, or so, we see it as a pretty natural extension of the previous models at setting max coverage. All right, and how are we going to accommodate deletions? Well, we're going to do this with linear sketching. So what are linear sketches? These are pretty powerful tools that can be directly applied to turnstile streaming, which is sort of the setting we're talking about here, but you can also apply it in a number of settings, including like distributed settings. And the general idea is I'm given a big matrix A, and I want to compress it while still retaining some like desired property or some sort of information. And I'm going to do this by multiplying it by a smaller linear sketch S. So here I have A. We have an n by d, and again, in general, we're thinking usually in the case where like n is much small, or sorry, n is much larger than d, so n is sort of the dimension I want to suppress here. So I multiply on the left by my linear sketching matrix S. K is also going to be much smaller dimension. Like for anyone who knows like count sketch, like a typical count sketch dimension for a lot of applications, like 1/epsilon squared, for example. And this is going to give us this much smaller like matrix. Okay, and what properties does S have? Well, first, S is going to be drawn from a family of random matrices, and this family is going to be independent of A, which crucially means that I don't need to see the contents of A and then create S, right? And second, it supports linear updates, that's why I call it linear sketch. And all this is saying is, okay, let's say I have some update Cij. This is going to say, okay, increment or decrement like one entry of my matrix A. Sketching A updated with C is the same thing as already sketching A, now sketching my new update and then just adding these two points together. And so you can see that this is really easily supporting insertions and deletions, right? I get an entry, I just sketch that like update, and then I just add it to my current sketch at the time. So this is just the visual representation. I have SA, an update comes in, I sketch it, and then I have successfully maintained my sketch. And right, so why are these two things important? Well, all of this is saying is that I can store and I can query SA at the end, and I never require like storing A itself in the entirety, right? So all I'm storing is basically like a K by D. And you know, for anyone who caught it, like you do have to in some way store S so that you can sketch these updates, right? But crucially, like S, we visualize it as a matrix to like keep it in our heads, but usually you're actually storing this super randomly. So for example, count sketch, you don't normally store it as the matrix form, you store it as like a bunch of hash functions that are going to represent what you're doing. That's not too important. All right, so what is our actual main theorem? Well, we're saying that we create a linear sketch of size until d, so that if you can run basically, you know, the classical greedy algorithm on this sketch instead of your original universe, then you produce a 1 minus 1/e minus epsilon approximations. And they're optimal with high quality. And all this is saying is that I can directly apply this in a turnstile stream, right? My sketch handles insertions, deletions, and that's what I have a turnstile stream. And so this gives me my stream. Any questions before I start to get into the actual technical stuff? Yeah.
Is there like maybe an epsilon factor hidden in the size of the sketch or?
Oh, yes, I forgot to mention that. So like in the results page, as I said, like this is going to be a d over epsilon to the third. I should have mentioned this, but I will start suppressing epsilon terms just so like it's not, you know, super cluttered, but yeah, there's an epsilon to the third there.
Nguyen, what was the result of Hoai-An years on? You
Um,
mentioned the D and something that.
yeah, so they give the same approximation and the same space up to like polylog factors maybe, and they're in like the insertion only. They're in the insertion only, but still edge right. Yeah. Okay, so what's our plan? Well, from this BM 17, they show that for a specific subgraph G star that they construct of the original graph, if you run the greedy algorithm on G star, then this only loses like an epsilon in your approximation overall. And so first what we're going to do is we're going to show what G star is, right? And forming G star, like when you have direct access to A in memory, is sort of trivial, but we're going to do it in such a way that will make it like easier to translate to a linear sketch. So I'm going to show how to do that outside of the stream. And then we're just going to show how to form G star like via a linear sketch. And that will be sort of the end, right? We just run the classical greedy algorithm on there and then we're good. Yeah.
What is the number of edges?
So the number of edges in G star will be D.
Okay.
D polylog, yeah. Okay, so what is G star made of? It's a pretty simple like structure or a pretty simple subgraph. Okay, so just a reminder that G is a bipartite graph, items on the left, subsets on the right. And I'm going to take a hash function h, and I'm going to map each of my n items to between 0 and 1. Really, you can just think of this as a permutation on the items. The hash function is just for the purpose of space. In the order of the permutation now, I'm going to add that item, and I'm going to add any dk of its edges to G star. Okay, so what I'm saying is like I have a permutation of items. As I go along the permutation, I add that edge and d over k of its edges. Obviously, if I don't have d over k edges, then I just add how many edges I have. And I just continue doing this until there's d edges of G star. And this is just all that comprises of G star. Anyone have any questions about this construction?
Is it your start epsilon?
Yeah. It's it'll really be like d epsilon to the third, or d over epsilon to the third. Yeah. Okay, so I'm just gonna give a very high level proof idea of what of why G star only loses like an epsilon factor, basically. And okay, so what they do is they start with an intermediate subgraph, and they say, take my original graph G, now form GP. All I'm doing here is I have my permutation over my items, right? And at some point in the permutation, I just like stop. And I just add the items and all of their edges. Okay, so no cap for now. And so if you think like, okay, this is my graph. Let's say for whatever reason, like A, C, and F were the ones that I'm gonna pick. So I delete everything else and I add all these edges into this GP structure. Okay, and for a sufficiently large P, aka like if I add and do this with enough items, then I only lose like an epsilon approximation. And this is like a fairly standard argument using like concentration bounds. But what's the issue? Well, the number of my edges can still be really large. They say it can be at like, at least n times k. And you can think of this just intuitively of like, I can have certain items that just have a ton of edges, right? And now I'm adding this item and I'm adding all of its edges to my sketch, and this sort of blows up the space. So what's the next thing that they do? Well, we have GP. Let's form GP prime, okay? And now what I'm going to do is I'm going to enforce an upper bound on the degree of my items. Now we're seeing how we're sort of moving towards the final construction. So again, I have GP. I'm saying, okay, let's enforce an arbitrary upper bound of 2, for example. So these are the edges I'm going to delete. And now you can see, okay, I've kept 2 edges from each item, and now this is going to be GP prime. All right, again, you're only going to lose an epsilon factor here. And in fact, they show that if you pick a really good value of P, you only will then have O tilde of the edges. What's the problem? Well, this problem of P actually depends on the value of opt. And we don't know opt in the beginning, right? We don't actually know anything. And so then, again, they transition from GP prime to what we call G star. And all this does is you don't choose a value of P, you just enforce the limit on the total number of edges. Okay, and that's how we got to G star. Does anyone have any questions about that? Cool.
So you might take like one where it's a lot of edges and for then like vertices afterwards because you'll reach the
so you are only going to be adding a subset of items, but because you're enforcing this upper bound, right? Like in the first, GP that they have, well, the issue is that you want to do this for enough items. I'm going to say if I add enough items and all their edges into my subgraph, then I only lose an epsilon factor. But yeah, the issue is that the edges there's too many, because you can have some items that just have tons of edges. And then they basically show like, okay, you don't actually need like every single edge for all these items. In fact, you only need D over K for the minimum between D over K and how many edges you actually have. Does that make sense? Yeah.
Sorry, I'm a little confused when you said from GD prime you're forming one the number of edges, you said it was 2, right? Even for these constant of ones, you still lose only out of epsilon factor.
Oh, sorry, I just did it for the picture, like in this picture, if you take like K to be, like K to be 2, then like D over K is 2.
There is some particular range of the horizontal radius.
Yeah, like it's specifically you want D over K edges, like for each item.
Okay.
Yeah, so no, it's not just for like any.
Yeah, that's why I was edit.
Yeah. Okay, so we know we want to take G star. How are we going to form this? Again, I'm going to form this outside of a stream. So for now, just take yourself out of the streaming context and everything. And this is going to seem like a weird way to do this when you have direct access, but then we're just going to show we can really quickly translate this to a linear sketch. Okay, so what is the first thing we're going to do? We're going to subsample vertices with rate 1/2 to the m star. Just m star will be defined in 2 seconds. And we're going to add these vertices and all their edges to an intermediate graph, GI. And let's say that we assume that we know some m star such that when I'm subsampling, now my opt and GI is around k. And here, opt just means like the maximum number of items that I can cover with k subsets. Okay, so I had probably a larger opt in my overall graph, and now all I'm saying is I'm going to subsample down such that my optimum answer in this intermediate graph GI is smaller and is actually k. Does that make sense? All right, so again, like all I'm doing is, let's say this is my G, and let's say for k is equal to 2, I mean, the 2 doesn't really matter, but I'm essentially I'm just subsampling some number of vertices, and then I add all of their edges. This is going to be GI. And equivalently for the matrix, if you like this better, I'm just subsampling some of the rows. All right. And why do we do this? Well, in McGregor, Vu, and 18, they have sort of a fairly somewhat standard proof that you can use turnoff with limited independence. And if you subsample down such that your opt is equal to k, that the sizes of the union sets over k subsets is preserved. All this is to say is that if you run the greedy algorithm on GI instead of G, you're only losing like an epsilon factor. And we just say epsilon over 2 so that we can weigh things properly. All right. Any questions so far?
Yeah.
You guys same as the GP thing you define gives size back, right? Just sampling some vertices and all of the edges.
Yeah, exactly. Yeah, I guess it's just that like it's the same thing, but it's just that like it's such a G such that we have an opt as the certain, like opt is k.
Yeah.
Yeah, but yeah, that's exactly right. Okay. So now we're going to form G star from GI. So what we're going to do is we're going to take, some constant times k colors, put 10. And for each item in GI, I'm just going to randomly pick a color and I'm going to color all of its edges, that color. Okay. So let's say this is GI. Okay, for A, I'm going to randomly pick one of the 10k colors I have, and let's say I pick purple. And now for C, I'm going to pick a different, like some color. D doesn't have anything because it's lonely. And E, okay, I know that we have 10k colors and this is unlikely, but this is just to show like we are not just coloring each vertex a different color. In fact, you can have vertices that have the same. Okay. And so let's initialize G star. And now for every single color, arbitrarily pick D over K edges with that color and add it to G star. Okay, and so what are we doing here, right? We're essentially throwing all of these vertices into like K buckets, I like to call it. And we're just taking D over K like samples from each bucket. Does everyone sort of understand what I'm doing? Cool. And then now I'm going to actually prove why this works. Like, why am I actually getting G star? from this. Okay, so for example, if I have d over k is equal to 2, well, okay, for the purple ones, I'm just gonna pick these two arbitrarily. For the green, I'm gonna pick these two, and that's gonna be what G star. Or this is what I'm trying to form G star. Okay. All right. What is my proof step? Well, first, I'm assuming, and also I know that the GI that I start with has an op that's equal to k, right? And so what I want to do is I want to build G star. And how do I want to build G star? Well, I'm going to classify items with degree that are greater than or equal to d over k as large, and all the other ones as small. And these are the items specifically that are like in my GI, right? Okay. Now I want to prove that there are at most k large items. And I want to prove that there are at most d edges among small items. When I can prove these two things, I can now say that each color does not actually have too many edges that are colored that color. And therefore, with like high probability, what I should be getting is I should be getting all the edges from my small items. And then for any of my large items, I should be getting d over k of its edges. So first, does everyone agree that like if this statement is correct, then I have formed G star? Okay. Any questions? All right. So really all I'm saying is, okay, right? I have an upper bound on my large items. I have an upper bound on the edges between the small items. Well, if I have an upper bound on these things, then that means that when I have k different colors, basically, like hopefully my items should sort of be well distributed in some sort of way. And if they're well distributed amongst the colors, then if I run d over k samples for each color, then I should be able to get the edges that I want. Okay. So for example, let's say we have GI. I'm going to show you in the ideal world or with high probability what is the action. Okay, so we have GI. And I start off with my graph. And this is like a coloring that is maybe more likely. And so I color these things. And so what happens? Okay, for purple, I want to pick two things, right? But remember, like d over k is 2 in an example. For the green, I picked 2 edges. For the pink, I mean, I didn't have 2 edges, so I just picked one of them. And so what has happened? Well, what I wanted to argue was like my items are generally well distributed. And for my large items, which in this case are A and C, I got d over k of their edges, which is what I need for G star. And then for the small item, I got all of its edges. It was just 1. Yeah.
I'm just using lots of word effect.
Okay, so what I'm trying to prove here is that maybe it'll make more sense when I go here. Okay, so if you remember, I'm taking a bunch of colors, 10 times k, and now for every single item, I essentially color that vertex with this color. Okay, and now for every single color, I'm picking d over k edges, and that's what I'm going to find in my final solution. Okay, and so what do I want? Well, when does this fail? This fails in sort of this setting here. When I have too many edges of the same color.
So in the end, what do you want? That for every high degree vertex, you have d over k edges, and for every low degree vertex, you want edges.
Right, because yeah.
That's what you're trying to do with this stuff.
Yeah, because to form like G star, what I'm saying is for every single item in some permutation, I want to do everything right? And so like, yeah, when does this coloring fail? Well, it fails when I have too many items or too many edges really that are colored the same color, because now I'm only taking d over k edges and I might lose too many, right? So I just want to argue in some sense that like, I have enough colors, A, and then I'm like distributing my items sort of among my colors in a good way. Having questions before? now I'm gonna start proving sort of those bullet points that we were talking.
So these
Yeah.
people know and stuff, like, we just assume like we know it, but we don't.
Yeah, so it's gonna pop up in a slide when I show that you implement streaming, but basically you do this somewhat standard streaming thing where you subsample and like log in rates. So you know how I say I subsample with, anyway, why don't you let me explain that once I get to that slide and then I'll explain it more in depth. Okay, so we know that we have these things and okay, so in general, right, if this is all correct, what I've just said, then I lose like an epsilon/2 factor from going from G to GI. This is just that sum sampling down to that universe. Then I lose another like epsilon/2 factor going from GI to G star. And so then all I have to do is run the classical gradient algorithm on my G star, I get my approximation. Cool. Okay, so let's prove this statement. This is essentially going to be approved by contradiction, and it's because I know that opt is a certain number. Okay. So let's suppose for a second that there are L large items. And remember, large just means that I have more than D over K edges. And I want to choose a subset that covers like C1 large items. Okay, choose any subset. I cover, you know, this number. And let me remove the subset and all the large items that I've just covered. And I'm just going to do this K times. Okay, so what does this look like? I mean, this sort of looks like kind of like the greedy algorithm, right? But I'm choosing it in some sort of way. So let's say I choose one. So now, what do I cover? Well, I've covered one large item. Let's say all these items on the left are large. And now I pick another one. Okay, I've covered another large item. Well, what do I know? I know that my opt is K, right? If you subsample down to this universe, my opt is K. And so additionally, I know that all these large items that I covered, C1 plus C2 plus C3, all the way to CK, is going to be at most K, right? Like, otherwise this would already directly contradict opt. All right. And for the purpose of contradiction, let's say that L, you know, the number of large items is like 10 times K. And okay, let's subtract these two numbers. So, you know, I have 10K minus K. It's going to be, I don't know why it says greater than, it's equal. But basically, I have at every single step, right? Remember I did this step for K things, I found a subset. For every single step, I actually had 9K additional large items that I didn't cover. Does everyone see that? Like, the K things that I covered in C1 through CK, okay, I covered these large items, but now I'm saying the number of large items that I have is actually 10 times K. So therefore, every single step, there were 9K like items that I never covered. And remember, large items have D over K edges, at least, right? And so this means that at least at every single step, I should have 9D edges among large items. All right, so what does this mean? That just by pigeonhole principle, okay, that at every single step, I should have been able to cover an additional 9 large items. And this is not like 9 in total, this is 9 in the first step, 9 in the second step, 9 in the third step, 9 in the fourth step, etc. Right? And this gives me like that I'm covering 9K large items. But I originally said opt was K, right? So this can't be. Does everyone understand? Okay, cool. And I'm not going to go through the entire thing for the purpose of time, but we also prove that there are D edges among small items, but this follows by sort of, I'm sorry, like a very similar argument. And so I just proved that there are most K large items, proved that there are D edges among small items. And now I want to just prove that each color does not have too many edges, based off of the fact that I just proved these two previous statements. Okay, so what are the things that I want? Well, I want every large item to be a different color with high probability, right? The moment I get 2 large items that are the same color, I risk like not getting D over K edges for one of my large items, or maybe even both. Okay. What are the other things that I want? Well, I want small items also to be a different color than large items. Okay, if I'm a small item and I'm in the same color as a large item, well, I might get none of my edges same, which is a problem. And in addition, I don't want like too many edges from other small items to be the same color as me, because then I sort of run into the same issue. And okay, this might not be true for one iteration of my coloring scheme, right? Like if I sort of color all my vertices and then I pick the D over K arbitrary things, well, like all these statements are not necessarily going to be true with more than like constant probability. So all I'm going to do is I'm just going to repeat this log D times, the whole coloring scheme. And I'm going to just take G star actually to be the union of all the edges from all my iterations. So what all this does is that it gives me these statements in the beginning with high probability, and it just blows up my space by like a log D factor, right? So it doesn't really matter. All right. So I proved all these things. And so now I proved that, you know, I should be getting D over K edges from my large items because they're not, sorry, I keep on using hash, but they're not colored the same color as other large items. And they're also not going to be colored with like too many small items, same with all the small items. And then for my small items, well, I said they're not going to be colored the same as a large item, and they're not going to be colored as too many other small items. So I should be in a color where I can get all my edges. All right, so that is sort of the end of just forming G star. Does anyone have any questions about that, about the correctness? All right, if not, now I'm just going to talk about how we can turn this into a linear sketch. This part should hopefully not be super long because we're almost going to directly translate what we just did with just some, sketching techniques. All right, so recall that we wanted to form our intermediate sketch from the following process, right? We subsampled with M star, and we assume that we know M star such that the opt is K. We can do the standard thing where we can just find M star by subsampling in like log n rates. This is basically essentially you're almost like binary searching for the correct rate, right? And you sort of run in all these parallel instances, and then you just pick the best instance at the end. And what are we going to do? Well, sorry, and did that answer your question? Did you want me to go more in depth about that? Okay, cool.
You still need to find each template or like. Are you deciding to reach the point?
Yeah, so what you're going to do is you're going to subsample your log n rates, and you're going to do this whole process for every single rate. Okay, and first this only blows up my space by like a log n factor. Now at the end I have a bunch of instances or a bunch of sketches, right? And so first I'm just going to terminate all the things in which, and really what I can do is I could just run maybe greed, for example, on or something, and I can just terminate all the instances that had an opt bigger than K because I said that couldn't happen. And then of the other ones, I just take the best answer, for example. And this just only amplifies by log n. Okay, and the second thing is that I can't like explicitly store GI, right? I go from G, I want to go to GI, and then I want to go to G star, but I can't really store GI like all at once. This is going to be way too much space. And so really what I'm doing is I'm going to keep track of what vertices that we've subsampled with the hash function. So this is going to really reduce my space there. Okay. And now, remember that we form G star from GI with the following process, right? We do this coloring thing. We take the colors, we pick each item and we color all its edges. For each color, we pick D over K edges, that color. So what are we going to do in the sketch? Okay, we're going to instead take K buckets. This should say 10 times K buckets. My buckets are going to be my colors. And now I'm going to use a hash function to map items to buckets. Okay, So essentially, I'm gonna hash my items to my buckets, but I'm not storing all the item explicitly, I'm just storing this hash function. And in each bucket, I'm gonna run d over k independent L0s. And for anyone who doesn't know what an L0 sampler does, all it does in this context is it's gonna uniformly sample an edge from the items mapped to that bucket. Okay, so this is almost the same equivalent as the coloring sort of scheme, but in this case, I have my buckets. I'm sort of throwing items into my buckets. So you can say I'm throwing items into my colors, for example. And now in each bucket or in each color, well, I'm like sampling d over k of the edges. Yeah.
So, how many vertices are there in GI? Like, the reason you're doing the bucketing is because there are too many vertices. And, a lot of them might be empty.
Yeah, exactly. So you might have so recall like before we bounded the number of large items and then we just bounded the number of like edges among small items. So you can't actually really have a meaningful upper bound in the number of small items because you could just have a ton of small items, but really what matters is like the edges, right? So like, yeah, exactly. You're gonna be like hashing a bunch of like, essentially like things with no edges into these buckets and it doesn't matter. Okay, so just to show this pictorially, we have we subsample down, to some universe, AI. And now I'm gonna hash these rows to like my buckets. I'm just gonna have k is equal to 2 buckets just for the picture. Let's say I hash the first row, the first bucket, second row, the second bucket, so on. And then here is, okay, and remember, like, I am not explicitly storing this boundary. It's way too much space. But I just want to show what I'm implicitly storing, right? I'm storing the hash function that just hashes. But in your mind, imagine the vector, and these are just the concatenated vectors, right? So take, for example, in the first bucket, I have A and E. I'm just like literally concatenating this into a longer vector. Just because for L0 samplers are like defined on the vector. And okay, let's say I'm L0 sampling 2 items, so d over k is equal to 2. And so in this case, okay, I randomly am picking two of the edges, right? I'm like 2 of the edges, well, like 2 edges here. Does that make sense to everybody? All right. And so basically, correctness essentially just follows from everything. So I'm just going to talk about the space. I have a constant number of hash functions, just using like log space. And my main space is coming from my 10k buckets. Each of them has d over k L0 samplers. And a really nice result from Hoai-An and Taros says that if perfect L0 sampler doesn't mean anything to you, it doesn't really matter. They have perfect L0 samplers and they only take polylog space. Okay, so that means that I can store dk L0 samplers in k buckets and I only have O tilde space. Yeah, so I think that's the end of like the max coverage results. How much time am I supposed to leave? 10 minutes? Okay, I'm just gonna really quickly go through the application just because I promised it and then I'll end.
All right, by the way, where's the epsilon in the space usage?
Oh, it's d over epsilon to the third.
Okay.
Yeah. Because like really what we need is like I'm hiding like epsilon in log terms into d over k and this k. Like it's not.
So it's d over k squared. No, d over k epsilon squared.
Yeah, exactly. And I think it's, if I remember right, I think it's like a d. Yeah, exactly. Like I have epsilon expressing. Okay, so the application I promised. Let's run through it. It's going to look really, really similar. Okay, in targeted fingerprinting, I have a matrix body. And now let's just say end users D features instead of items and subsets. And I'm going to have some target user U. And what do I want to output? Well, I just want to output like K features, so K columns, such that the number of users who share identical values with U is minimized. So I just want to separate U from everyone else. Show this in the picture, be easier. Let's say this is our target user. Let's just suppose that these are the 2 columns we're looking at. Well, I've separated B from every single person except for C, right? Like A has a 1 here, but B has a 0. Does everyone understand what I mean by separation? Cool. Okay. Why is this important? A lot of privacy attack literature stuff. We apply this application here. And what we're really trying to say is like, what K features have the greatest risk of like forcing, of allowing some malicious actor to re-identify someone based off of querying their features. And if you want to know more about the applications, I have it in my brain, but I will not say it right now. Okay, previous work just measures the risk of like fixed features. And so this is cool because it's kind of like we can dynamically monitor the risk. Maybe your data set changes and these K, things change, and now you can rerun this algorithm, you can figure this out. Okay, we have a direct reduction. All we're gonna do is, I'm just gonna skip through this and we'll show a picture. We have our target guy, and here, all we're gonna do is in every single column, we're gonna subtract off the value that B has in that column. Here, I'm subtracting off 0, so nothing happens. Here, I'm subtracting off 1, and so on. So this is sort of why A, it was important that we could have non-zeros, because this is clearly not a 1. And second, why it's important to have deletions, because we could not like simulate this in updates without deletions. All right, and now notice that for every entry in which I had a different value from the target, I am non-zero. And for every entry that I was the same as my target, then I have a 0. Okay, so now this sort of directly corresponds. Okay, cool. Open questions. Is O tilde D optimal? We're not 100% sure, but it seems like it might be the right answer. And then for the summary, okay, we create a linear sketch with a near optimal approximation factor and O tilde space. Really cool because we do turnstile streams. And then we reduce targeted. Thank you.